Good morning all. In this session, we will study the exponential distribution, which is an important continuous probability distribution which is used to model waiting times. So it is widely applied in real life situations such as reliability analysis, survival studies and service systems. The key idea behind this distribution is to measure the time between events that occur randomly but at a constant average rate. Throughout this presentation, we will explore its definition, properties and practical problem solving techniques. So a continuous random variable x is said to follow an exponential distribution with the parameter lambda greater than 0 if its probability density function PDF is given by f of x equal to lambda into e power minus lambda x such that x value is always greater than or equal to 0 and 0 otherwise. The moment generating function of the exponential distribution is given by mx of t equal to minus infinity to plus infinity e power tx into f of x dx. So here when we are deriving these equations of the limit 0 to infinity e power tx into lambda into e power minus lambda x dx, on integrating we'll be getting the moment generating function of x as lambda divided by lambda minus t, where the lambda value is always greater than t. So a continuous random variable x is said to follow an exponential distribution if its probability density function depends on the positive parameter lambda. So this parameter represents the rate at which the events occur. The exponential distribution is unique because it models the time until the next event happens. So it is always positive and decreases exponentially as the time increases. Only so we are saying that lambda is always greater than t. So this indicates that longer waiting times are less likely. So this makes it highly useful in modeling lifetimes of systems or times between the failures. The next one is mean and variance of the moment generating function. A moment generating function of the exponential distribution helps us compute important statistical measures like mean and variance, so which is derived from the probability density function and provides a compact mathematical representation of the distribution. So we'll be writing as 1 minus t by lambda the whole inverse. So when we are expanding this, so we get the summation of the values of 0 to infinity t by lambda power r. So by differentiating the moment generating function, we can obtain various moments of the random variable. So this function plays a crucial role in theoretical analysis and simplifies calculation in probability theory. So where the mean values given by mu and dash, that is the coefficient of t power 1 by 1 factorial, which is 1 by lambda, and mu 2, that is the coefficient of t square by 2 factorial, so which is 2 by lambda square. So the variance mu 2 is given by 1 by lambda square and the mean is given by 1 by lambda. So let us go with the problems. So here let x be a random variable with the probability density function f of x equal to 1 by 3 into e power minus x by 3, x value is greater than 0. We have to find the probability of x value greater than 3 and the moment generating function of x. So we already know that the lambda value is 1 by 3. So we have to find the probability of x greater than 3. That is the value of f of x that ranges from 3 to infinity. So where f of x is given by lambda into e power minus lambda x, we are substituting the values and we get the value of e power minus 1. So also we have to find the moment generating function mx of t, that is given by lambda divided by lambda minus t. So on substituting the values of lambda here, we get the moment generating function value as 1 by 1 minus 3t. The next one is very important property, memoryless property of the exponential distribution. So one of the most important characteristics of the exponential distribution is the memoryless property. So it states that the probability of an event occurring in the future is independent of how much time has already passed. So in simple terms, the process does not remember the past. So this is a unique feature among continuous distributions and is especially useful in modeling systems where past history does not affect the future outcomes. So here probability of x greater than k, that is from the value ranges from k to infinity into f of x dx, where the f of x value is given by lambda into e power minus lambda x dx. So the value of probability of x greater than k is given by e power minus lambda into k. So the converse of the above property is also true, that is the probability of x greater than s plus t divided by x greater than s is equal to probability of x greater than t, then x follows an exponential distribution. So this memoryless property can be mathematically expressed as the probability that x exceeds s plus t, given that it has already exceeded s, is equal to the probability that it exceeds t. So this shows that the remaining lifetime is independent of the elapsed time. So this property is widely used in reliability theory and queuing models, where it simplifies analysis significantly. Next problem is car battery example. So let us consider a practical example. The number of kilometers a car can run before its battery fails follows an exponential distribution with an average of 10,000 kilometers. So we are asked to find the probability that the car can complete a 5,000 kilometer trip without battery replacement. Since the exponential distribution models lifetimes, so we calculate the probability that the battery lasts beyond 5,000 kilometer. So this involves exponential survival function. So we know the mean value as 1 by lambda. So that is nothing but where the lambda value is 1 by 10,000 kilometers and x follows then exponential distribution. So the probability density function is given by f of x equal to lambda into e power minus lambda x. So which is 1 by 10,000 into e power minus x by 10,000. So we have to find the value beyond 5,000. So the limit value ranges from 5,000 to infinity into f of x dx. So on substituting the f of x value, we will be getting the value of the probability of x beyond 5,000 is 0.6065. The next problem, this is repair time. So in this problem, the time required to repair a machine follows an exponential distribution. So we are asked to find two things. First, the probability that the repair time exceeds 2 hours, and second, the conditional probability that the repair takes more than 11 hours, given that it has already taken 8 hours. So this problem highlights both the basic probability calculation and the application of memoryless property. So the function x represents the time to repair that machine, and the probability density function f of x is given by lambda into e power minus lambda x. So we are substituting the values of lambda in that equation, and we are asked to find probability of x exceeds 2. So the value is found to be e power minus 1, and we are also asked to find probability of x greater than or equal to 11, given that x value exceeds 8. So which equals the probability of x greater than 3. By memoryless property, we are applying this, and we are finding out the value to be e power minus 1.5. The next one, in this example, a watch has an average lifetime of 120 days, and we need to find two probabilities. So first, the probability that it fails within 24 days, and the second, the probability that it lasts at least 180 days. So this type of problem is common in reliability and survival analysis. So let the random variable be x. The mean is given by 120. So 1 by lambda is 120. Lambda value is 1 by 120. We have to calculate the probability density function. F of x is given by lambda into e power minus lambda x. So here we are substituting the values, and we are also asked to find the probability of x which is less than 24. So the limit value ranges from 0 to 24, and when we are integrating and we are finding out the value as 0.1813, so the probability it lasts for at least 180 days. Yes, the next one, probability of x greater than or equal to 180, which means that the limit value ranges from 180 to infinity. So, and f of x value is found out to be 1 by 120 into e power minus 1 by 120 into x dx. On integrating the value, you will be getting a 0.2231. The next one, we are finding the mileage which car owners get with a certain kind of radial tire is the random variable having an exponential distribution with mean 4000 kilometers. So the mean value is given here, and we have to find the probabilities that one of these tires will last at least 2000 kilometers and at most 3000 kilometers. So obviously you will be using the exponential distribution, and in the first case we will be using for at least 2000 kilometers. That's the probability of x value which is greater than or equal to 2000, and the next one at most 3000 kilometers, that is to the most 3000 kilometers. So that is probability of x which is less than or equal to 3000. So as like the previous example, so we'll be using the same exponential distribution here. We'll be finding the 1 by lambda mean value and f of x value, and we'll be substituting in the equations of the formulas. So yes, as I said, the probability of x greater than or equal to 2000, that is the limit value ranges from 2000 to infinity into f of x dx, and the value is found out to be 0.6065. and in the next sum, probability of x at most 3000. So the value ranges from the limit 0 to 3000 into f of x dx. On substitution, we will be getting the answer as 0.5270. Thank you.